Yeah, and take it away.
Great. Well, thank you so much for inviting me, Jonah. By the way, I'm Colin Schiebner. I work with Vincenzo Vitelli over in the JFI. So one nice thing about being virtual is that I get to hang out with the Kadanoff Center people more easily than if I was actually physically in the JFI and had to walk across the science quad. But at any rate, so it should be exciting to talk about some active solids with non-Hermitian elastic waves. And just to get started, so I'm thinking about active solids, and a lot of times when we think about active matter, we think about flocking or the fluid phases of active matter. But in fact, the solid phases have a rich phenomenology all of their own. So here's just a few examples. These active solids can be synthetic, so things that we actually build, like these pucks that are interacting via magnets on an air hockey table, or a robotic metamaterial where there's minimal electronics that couple to mechanical deformations and inject energy at the microscopic unit. And of course, they can also be living things, from, often from biology, such as a mound of fire ants or a swarm of living bees. And the thing I want to focus on today is what happens to the elasticity of these solids. How can this microscopic injection of energy change the basic structure of the elasticity, that is the relationship between deformation and stress? So to crack open this question, I want to begin by asking, what is elasticity? As you may know, there are many good books on the subject. I like this one, it's a classic, can't go wrong. And one of the key equations that really captures the structure of the theory is the following. Hooke's law, which is just a statement that stress is proportional to strain. And so there's really three key ingredients. There's stress, which is the current of momentum. So we're saying this is a system that has a conserved quantity, that being linear momentum, and the forces will be divergences of this current. And then what does the stress respond to? Well, it's not a fluid, so it's not about the deformation rate, although that could be there in principle in addition. It's about the actual static deformation. So when you change the shape, it doesn't like it and it exerts stresses, and that mathematically is captured by the strain. And so what Hooke's law is, it's a phenomenological statement that says the stresses will be proportional to the strain. And this stiffness tensor, this thing in between Kijmn, it's the proportionality constant between stress and strain. So you give me a deformation, I'll tell you how much stress that causes. And if you were to crack open Landau and Lifshitz, they'll tell you this about the stiffness tensor, also called the elastic modulus tensor, or just elastic tensor, that it has this symmetry. If you take the first two indices and swap it with the last two indices, are you all able to see my cursor?
Yes.
Oh, great, thanks. Or else this would be a lot more confusing. And swap it with the last two indices, it's symmetric. So why is that? Where does the symmetry come from? Why are Landau and Lifshitz telling us this? Well, if you're thinking about a passive material, one generally is the existence of an elastic potential energy. It may be a very complicated function of the strain, but for small strains, you should be able to approximate its minimum as a quadratic function. And so if you turn the crank of performing the variation with respect to the displacement field, you find that the stresses are this object right here. And what we recover is, of course, that the stresses are proportional to the strain, and we manifestly find that that object, Kijmn, is symmetric. Kijmn equals Kmnij. But for an active solid, this is not necessarily the case. Because the individual components have an internal source of energy, we can't necessarily start from this assumption that a potential exists. In this case, Hooke's law is the phenomenological starting place, because the stress-strain relationship can still be defined, but what we'll find is that the stiffness tensor now can be the sum of two pieces, an even piece, which is exactly what we had before, plus an odd piece, which is anti-symmetric under the interchange of the first and second pair of indices. So what does this buy us? Because this is all kind of indices and somewhat up in the air. So let's look at how this actually affects the structure. Here, I've been a little sloppy. I changed notation from K to C. Please forgive me, but C is the same tensor that K was in the previous slide. Once again, there's three pieces. So the strain, and for simplicity, I'll talk about 2 dimensions. And in 2 dimensions, strain is a rank 2 tensor, and so it's a 4x4 matrix. And it has 4 pieces. You can talk about dilation, which is the trace, rotation, shear 1, and shear 2. So dilation is a change of volume without a change of shape. Rotation technically is not strain, but it is a gradient of displacement. So for generality, I'll actually include it. And I'll think of this UMN as being, is strictly speaking, displacement gradient and not strain, but that won't play a major part in what I discuss. And then the shear is a change of shape without change in volume, and it comes in 2 types. You can extend horizontally along the horizontal axis and compress it along the vertical, or you can deform at the 45 and compress along the negative 45 axis. And you can stack those into a vector, and you can perform a similar decomposition with stress. So the isotropic part of the stress is the pressure. The antisymmetric part of the stress corresponds to a torque density. And then, of course, there's a shear stress and 2 shear stresses corresponding to the an impetus to perform those shear strains. And those can be stacked into a column vector. And then in this notation, this CIJMN, which was a rank 4 tensor, we can just represent it as a matrix. And each one of these question marks in this matrix is an elastic modulus. But in general, there's normally some sort of physical constraints that link these question marks to each other. They're not all independent. So to just take a very simple, concrete example, let's make 2 very concrete assumptions. First, let's assume that this thing is isotropic. So what will that buy us? That will buy us that the scalar and pseudoscalar degrees of freedom, they'll have to decouple from the 2 shears. And it also tells us that these 2 shears, which under rotation transform like a bivector, that the couplings must either be along the diagonal, like the identity matrix, or they must be anti-symmetric. So the 2 pink question marks must be the same, and the 2 blue question marks must be the same, whereas these 4 black question marks could all be independent. Now let's make a second assumption that you'll only really respond to deformation, so change in shape. So that excludes rotation. So not coupling to rotations means that this column must be 0. And voila, we've gone from having 16 question marks down to merely 4. Now let's give these names. Some of them are familiar. For example, this bulk modulus is there in a standard solid, and it corresponds to when you squeeze or dilate something, there's a restoring pressure. Likewise, the shear modulus resists shear. So when you try to pull it sideways, it wants to contract back in. And likewise, along the 45 diagonal. But now there are these question marks that have something different, right? Notice that both the bulk and shear modulus, they respect the symmetry of this matrix, which corresponds to the symmetry of this elastic modulus tensor. And as a result, they can be there in passive solid. But since we're breaking the major symmetry of this elastic modulus tensor, that means we're breaking the symmetry of this matrix. And so new elastic moduli can emerge. This first one, for example, couples dilation to a torque density. But notice that there's still no coupling between rotation and stress at all, because we have zeros in this column. Likewise, there's this modulus that resembles the shear modulus in that it couples the shear stress to shear strain, or sorry, shear strain to shear stress, but it does so in an anti-symmetric way, and we'll call it K0 or K odd. And notice here that unlike the regular shear modulus, where the stress represented by these blue arrows is always parallel to these black arrows, the K naught rotates the blue arrows 45 degrees clockwise with respect to the black arrows. So it's this chiral coupling in the space of shears. And I should have mentioned at the beginning, but feel free to interrupt at any time if you have questions or if there's something you want to ask.
Okay, so since you did say that, this could be a naive question, but you previously said that C could be, or I guess K before,
yeah,
either symmetric or anti-symmetric, but this A term seems to be breaking either of those. So could you explain what's happening?
Yeah, absolutely. So the full C can be the sum of a symmetric part and an anti-symmetric part. So you're exactly right to observe that when you put this A in, it's a bit unusual because we thought that maybe by adding activity or whatever, we would just add things to the anti-symmetric component, but it turns out that you can also add things to the symmetric component that are allowed simply because you're breaking the symmetry. But yeah, so the full physical elastic modulus tensor would be the sum of the symmetric and anti-symmetric parts. Weird passive coupling to rotation, but indeed that's not physical because the actual physical stresses are going to be the sum of the two. So you could still respect this modest assumption of not coupling to rotation. But yeah. Anything else? All right, then I'll carry on. So correspond to some sort of source of energy. How do I know, for example, that they're not just dissipation, that's not their origin? So let's think about this. I'm going to do something that seems at first glance maybe a little trivial. What I'm going to do is I'm going to take a little differential of my solid, a little patch of material, and then I'm going to deform it. I'm going to deform it along a cycle. So the first thing I'm going to do, and I'm just going to use shears for simplicity. You could also incorporate dilations or whatever you want to do. First, I'm going to shear it horizontally. Then I'm going to, in addition, shear it at a 45-degree angle. I'm going to undo that initial shear I did. And then I'm going to come back to my original starting place. And now I'm going to ask a very simple question that is, let's compute the work. how much work did I do? Well, the work done by the, or in fact, on the elastic solid is the stress dotted in to the change in strain. So that's the differential of work. And to compute that on the full cycle, I simply integrate stress over strain. And then I utilize my constitutive relationship. I can write this stress as the sum of two parts, CO times Uij, and then CE times Uij. And what I find is the following. So first, we know that since the even part can be derived from a potential, and I started and ended at the same place, that work is equal to 0. But if I take a closer look at what's happening in the anti-symmetric part with the Ki, we find that this is a non-vanishing cycle, right? So the total work done, if you do this quick calculation, it's equal to 2k0 times the area enclosed in the space of strains. So this implies that the material is acting like a distributed engine, right? So I can take a little differential of my material, force it through a strain-controlled cycle, and that strain-controlled cycle will extract energy. That tells me that to have these moduli, there must be a microscopic source of energy. And in fact, you can run the cycle in reverse. If you do it in the opposite direction, you're injecting energy into the solid. And so there's a sense of energy absorption. But what's actually somewhat interesting, even from a practical point of view, is that notice that strain rate does not appear anywhere in this equation. It's purely a geometric relationship. So the amount of absorption or release is independent of rate. This is unlike a viscous material like a gel or a fluid, or most solids have some element of viscosity. Here, the work extracted or injected is independent of rate. So let's talk about, this has all been in Continuum. Let's talk about what's hiding underneath. So for
Sorry, can I ask you a question?
Yeah, of course.
Sorry, I joined a little bit late, so maybe this is a dumb question. So you just said it's, so yeah, this cycle, this is just a geometrical thing. Does that mean you can just pulling energy out like as fast as you'd like, or?
Yeah, well, so at some point you would have to consider some sort of other physics. If you go at the speed of light, you're going to need a relativistic theory or whatever. And most materials are viscous, right? So that the constitutive relationship that says stress is proportional to strain, that's only approximately true at slow rates, essentially. So if you're moving at a very fast rate, there'd be some viscoelasticity, and that viscosity would play a role. So, I mean, if you're thinking about what's the efficiency in the context of an actual realization, those factors, to have realistic, continual modeling, those factors would have to be incorporated. But to any regime at which the equations I'm writing down are physically realistic for your realization, then yeah, it is saying that you could extract the energy as fast as you want.
So I guess I'm wondering then, so like each square centimeter or whatever of the system has a certain amount of energy being put into it each second. And so does that then, so the thing that's stopping you are things like viscosity or something, some time scale stuff. Does that mean that there's a relation between how much energy you're allowed to pump into the system and how much, like, say, I don't know, viscosity there is? It seems like that would then set some sort of equality. I don't know.
Yeah, exactly. And that's actually something that we've looked a lot at. And actually, I'm going to show you some things that relate a lot to rate and energy balance in just a few slides. But yeah, you're absolutely right. And in general, solids come in all shapes and sizes in terms of what the actual empirical relationship is between viscosity. There's power law solids, and various different sorts of semi-empirical relationships. And yeah, so it comes down to what the actual source of the dissipation is. And of course, there's a second issue, is that if this is powered by batteries, let's say, there's another time scale essentially set by, when's this battery going to run out of energy? Or if it's a biological creature, when does that biological creature get tired, right? And so there's also that time scale that, unless you have some endless source of energy, there's this constraint. But if you're at a low enough frequency and at time scales for which it's reasonable to think in this way, then yeah, you can continue to extract energy repeatedly.
Great. Thank you.
Yeah. So let's think about a regular elastic solid. And kind of the cartoon picture, at least that I have in mind, and that if you open the textbook on elasticity, you may see, is that mechanical solids are networks of masses connected by Hookean springs. Now, I'm not an atomic physicist, but I don't think this is actually true. So, why do we use this model? Well, it turns out that the Hookean spring is not just a random choice, but it's actually the most general linear approximation to any pairwise interaction that does three things. It conserves linear momentum in that the forces are equal and opposite on the two participating masses. Secondly, the force only depends on the length of the bond, right? It doesn't, for standard Hookean spring, it's not about the strain rate, it's about just the change in length, not the change in orientation or the velocity of the particles. And the third thing that the Hookean spring builds in is that it conserves energy, right? You can write down a potential that's 1/2 kx squared. And what we want to look at here, because we're looking at elasticity, conserving linear momentum is built into the formalism right away because we're studying a stress tensor. The change in geometry is something that we also want to keep. So we want to throw away one and only one of these properties, and that is the presence of a potential energy. And when you do, what you find is that the most general interaction is simply a Hookean spring plus this additional piece, which is transverse. So a normal spring would push back along the bond vector, but here the force is transverse. Again, when you elongate, the force is still proportional to the change in length, so the direction flips. And we can represent this by this equation. And unlike a Hookean spring, which just has one parameter, the stiffness K, there's an additional spring constant KO that sets this transverse force. And how do we see that this is actually active? Well, microscopically, I can go along a path that resembles the one I did in the continuum. I can first rotate, no work done. Elongate, only the passive part would care about that because I'm moving radially to the bond. But now the active part has instigated a transverse force. And when I go along that transverse force, work is done. And then I return to my initial configuration. And we notice that this work that went out has no compensating energy going in elsewhere. And so that we find that microscopically, the work is equal to K0 times the area. And this works because the beam violates energy. Reciprocity being the fact that if you compress the bond, it wants to twist. But if you twist the bond, it doesn't care, right? There's no response to that.
Sorry, can I ask another question?
Yeah,
or I guess it's a comment. So I know, so people in Heinrich's group, I think, started working on, there's some project with some springs, but anyway, just in the conversation, I think that there's another resolution of this, which is that K0 is not constant, so that it's not actually a linear system. And so like you can but it's nonlinear.
Yeah, so, well, yeah, so it's an interesting question. So everything I'm doing is linear, right? So, but you can certainly, yeah, gain and lose energy by having other forms of hysteresis or rate dependence. But yeah, if you're restricting yourself to linear case, that's really all there is to get these transverse forces. But even in a nonlinear sense, if you could do a cycle that extracts energy, then I would expect actually some of the subsequent things I'm going to talk about to actually be there, even if they don't appear immediately in the linear analysis. But yeah, it's an interesting point that if you consider nonlinearities in the spring, it opens up a whole new avenue for discussing these interactions.
I guess I was saying that you can still have conserved energy by using those nonlinearities. So
well, so are you saying that the linear theory would be compatible with the equation I wrote down, but somehow the nonlinearities would save you, would compensate for this?
Mm-hmm. I don't know for sure, but
yeah, well, it'd be really interesting to look at that in more detail. I would be a little skeptical that if this linear theory was actually valid, that the nonlinearities could save you, because they're going to scale differently with the size of the cycle, right? So if those nonlinearities perfectly balanced at one value, then I scale my cycle down. I just make it a little bit smaller. Those nonlinearities should be suppressed faster than the linear terms. So, so I think there is something robust about saying that if this is your linear theory, then you should be able to, at least for a very small, some range of validity, extract this energy. But I mean, I'd be happy to entertain different ideas about how that could be compensated.
Thanks.
Cool. So what was I? Oh, okay. Let's continue. So here's just a little cartoon. I don't think this is the simplest way to contrive one of these things, but it certainly works. What you're looking at is a fan system mounted on a spring, and these batteries constantly power the fans to blow, but there's a gear system, right? So as the beam elongates or compresses, these fans rotate and create these transverse forces that are proportional to the amount of displacement, at least linearly. And so we can put this on a lattice, we can coarse grain it, and indeed, for a triangular lattice, we can compute these moduli in terms of the added parameters. You can even do it on a honeycomb lattice. So, but enough about statics. What we were really interested in is what are the dynamics? So here's just a standard elastic material. And if you consider an inertial equation of motion, so some force density given by the divergence of the stress is equal to the mass times the acceleration, then you can have acoustic waves, and they look like this. So the arrows are the displacement field, and the black lines are contours that would be straight in the undeformed material, but are deforming because a wave is passing through. And why does a normal material do this physically? Well, it's because there's a shear modulus or a bulk modulus. They both contribute if you were to consider longitudinal waves. And those moduli say, hey, I don't like being deformed, so they push back. When they push back, the system overshoots its initial configuration and the cycle continues. One way to get rid of this is to consider an overdamped equation of motion. So imagine this thing is on a substrate and there's a lot of drag so that the force is actually proportional to the velocity. In this case, the elastic energy does not get converted into kinetic energy. It just gets, it just peters out and no waves propagate in an overdamped regime. So let's consider a solid where that's overdamped, has no shear modulus, no bulk modulus, and the only thing it has is this K for simplicity. Even though it's overdamped, we find that indeed the wave can still propagate, right? And to get a little insight into what exactly is going on here, what we can do is color each of these ellipses by the strain and then the stress. So that's what the ellipse and stress icons represent. And so if we were to plot that strain in the cycle of strain space, what we find is that it indeed traces out circles. So autonomously, this shear is tracing out a cycle in the strain space that corresponds to work being injected that offsets the dissipation. And just as related, but not exactly the same to a comment that was raised earlier is, all right, can we balance dissipation with energy injection? Yeah, and in fact, you can do that. You can do some trigonometry to say, okay, what is the area enclosed here? How much work do I inject per cycle? And then you can think about one of these cycles of the actual displacement field and say, how much is the substrate friction actually taking out? And if you do that, you can deduce the speed of the wave and say that the speed is 2k naught over eta times q. By speed here, I mean the group velocity. And the thing I really want to emphasize today, though, is this notion of non-Hermiticity. So to kind of get into that a little bit, here's a little phase diagram. If you were to have these two moduli, K naught and A, and just normalized by B. And for concreteness, let's consider putting these springs on a triangular lattice. In principle, you could have whatever microscopic realization that you want, but let's be concrete. Then as you adjust this microscopic parameter, KO, you're going to trace out this line through the phase diagram. And the relationship between the forces for a plane wave, the relationships between the forces and the displacements is given by this matrix right here. And this is the dynamical matrix, and Q here is the wave number. So, well, we noticed one thing, that when A and K naught are 0, this matrix is completely Hermitian, right? It's a real symmetric matrix, it's Hermitian. And so its eigenvectors, which correspond to the modes of vibration, they're orthogonal to each other, right? So in this case, they correspond to a transverse wave that I showed before and a longitudinal wave. And what I'm plotting here is the state of this ellipse in strain space. And we see, if you consider overdamped dynamics, they'll just relax to 0. But now notice that when I increase K, I actually break the symmetry of this matrix. So this dynamical matrix becomes non-Hermitian, right? And at first, the eigenvectors will become non-orthogonal, and eventually they'll reach a point where the two eigenvectors become parallel and they coalesce. So if you ask for the two eigenvectors, you find that they're actually parallel to each other, and such an occurrence is known as an exceptional point. And if you go above that exceptional point, you cross between a region which you can call PT symmetric, if you want to use that language, or sorry, PT unbroken and PT broken. And what you find is that there's a finite oscillation that sets in. So the eigenmode went from being linear to having this circulating character. And if you go all the way to K naught at infinity, these waves become sustained because the energy injection offsets the losses from the substrate drag. But everything I just showed you is for an infinite medium, right? I took a Fourier transform, so it's either infinite or it's on some sort of torus or something like that. And the thing I want to get at that I've been thinking a lot about recently is what about the boundary? What happens at the boundary of such a solid? Does activity even play a role? And it turns out, yeah, non-hermiticity matters. So before I get into it though, I want to start with just even a simpler system. Before we do the elasticity, let's do something as trivial as we can make it. So what you're looking at here is a line of masses connected by springs, right? These are just regular Hookean springs. And these two masses are pinned at the boundaries, right? So I'm just going to say, you're not allowed to move, you're not allowed to move. And if I were to ask, can somebody please compute the normal modes of vibration of this system? You know, this seems like something that we should be able to do, right? It's just a linear system. Doesn't get too much easier. And the first thing that you might do is say, okay, I can write the forces as, you know, a sum over all positions times this dynamical matrix. And then you realize, all right, so this is just a problem of finding the eigenvalues of this dynamical matrix. And if you're like me, you say, oh my, that's actually kind of hard. I need to make this even simpler. So what I'm going to do is I'm going to pretend that actually I don't have clamp boundaries. I'm just going to pretend that if my system is really large, maybe I can just approximate it as being periodic. Because after all, right, if I had 10 to the 23 particles, making this thing periodic, you know, I have 10 to the 23 non-zero matrix elements corresponding to these bonds, and I'm just going to change one of them by, you know, linking it up to its neighbor. So it seems like it should be reasonable that pretending that this thing has periodic boundary conditions should give me some reasonable approximation to the spectrum. And what's so nice about periodic boundary conditions? Well, it allows me to take a Fourier transform, right? Because I restore exact translational symmetry. I can represent this thing in terms of a wave number k, where I'm using a basis of eigenmodes that looks like this. And then even I can compute the spectrum, right? It looks like this. And then if I were to plot this in the complex plane, I'll talk about why I want to do that later. It's D is Hermitian, it lies on the complex plane. And then there's one little subtlety that we have to think about, is that this basis right here, it's great for translational symmetry because these Fourier modes, of course, are the eigenvectors that diagonalize translation. It's not great for boundary conditions though, right? Because actually the Fourier mode in general is non-zero at the boundaries. So the basis I've introduced doesn't gel great with the boundary conditions I want to meet. But nonetheless, like I said earlier, if I'm really introducing, if I'm really only changing one of these matrix elements, then I would expect it to, I would expect this basis to at least resemble the one that has with the open boundaries. And for that to happen though, we do need to satisfy the boundary conditions. So that means two of these block waves, two of these Fourier modes, they have to interfere with each other. They have to destructively interfere at the boundary. And to do that, they need at least approximately the same lambda, because this lambda is going to set their oscillation in time. And so if they're really going to conspire with each other to meet these boundary conditions, they have to, at least approximately, they need to be able to interfere with each other and have the same lambda. But that's not a problem because I have a periodic spectrum and it's all confined to the real line. So every point except for these extrema, they're all going to cross, you know, they all have somebody else that they can interfere with. So great, we're in good shape. Now I want to just step this up a little bit in complexity, not a lot, and consider this system. So all I'm doing here is I have a very massive particle on the left, a very light particle on the right, and I'm going to have decreasing mass all the way through, just a constant rate of decreasing mass. And now if I wanted to do my same trick of putting this on a ring, it's not super clear how I would do that immediately because, I mean, the system's going to know when it comes back and has this sudden drop. So it doesn't seem like you could get much out of putting it on a ring. but we could still try to do that anyway. And the way we could think about it is, all right, if I'm modeling the accelerations, let's say, then I can just pretend that this is no longer a standard Hookean spring. Instead, I'll pretend that it's a spring that has a force such that you know, the force on the right is greater than the force on the left. So it violates Newton's third law. But on the bright side, I can actually, you know, I can make each of the springs follow this rule, and I have an imitation of this system on periodic boundaries. And now, if you were to go through the process of computing the dynamical matrix and finding the eigenvalues by taking a Fourier transform, what you find is that the spectrum looks like this. It no longer lies along the real line, because actually this involves a source of energy as well as a source of linear momentum. And what it does is it actually traces out an open arc. And when you go through the Brillouin zone, you never hit the same point twice. Now this is somewhat problematic, right? Because I said the whole thing that to satisfy these boundary conditions, some sort of physical interference is needed, and they need to be, two modes need to have the same lambda. But here, no two block modes have the same eigenvalue. And so I can also just compute the spectrum numerically or solve this exactly for the system with open boundaries. And if you were to do that, what you find is actually the spectrum does not resemble that of the Fourier transform. In this case, the spectrum lies entirely along the real line. So something about adding this this broken reciprocity, or equivalently, this broken hermiticity of the dynamical matrix really threw a wrench in the standard protocol of computing a Fourier transform and hoping that this the spectrum actually resembles that of the open system. And so let's take a closer look. This effect goes by the non-Hermitian skin effect. Goes by the name non-Hermitian skin effect. So typically, you introduce, when you do Fourier transform, you introduce this thing beta, which is e to the ik, and you're normally integrating e to the ikx. And so we can think about the Fourier transform. This is just nothing fancy going on here, just a way to think about the Brillouin zone as a circle in beta, right? So you can make this dimensionally correct by dividing by a lattice spacing if you want. And so as you go through the Brillouin zone, you trace out a unit circle in the space of beta. And this is for a 1D system also. Right, and then what is the dynamical matrix but a map? You can also think of this as a Hamiltonian if you like. But a map from this Brillouin zone to the space of eigenvalues. And if you have a non-Hermitian dynamical matrix or Hamiltonian, you'll trace out a circle, right? Because you can occupy the entire complex plane. You may trace out a circle. And so, and this is, if you're thinking about periodic boundary conditions, this is all you have. But if you have open boundary conditions, you realize that you can actually diagonalize the translation operator with a little bit more freedom. You can actually add this additional piece, which is a exponential localization to either boundary that would still respect translational symmetry. And what that corresponds to in this picture is deforming the Brillouin zone off the unit circle in the complex. And of course, we can perform an analytical extension of this D. And what we find is that these circles also have images in the plane of eigenvalues. And so what we can do is we can search for the perfect path through the Brillouin zone such that each of these modes deform to each other and they all find a partner that has both the same decay length and the same eigenvalue. And we call that special path the generalized Brillouin zone. And what you notice though is that to find this generalized Brillouin zone, I had to really deform this thing like a lot, right? There's an extensive number of localized modes. I didn't just take one point in the Brillouin zone and take it off. I had to continuously deform it off. So unlike a standard topological edge mode, where there's only a single localized mode or a finite number, a sub-extensive number, here we have an extensive number of localized modes as a result of this analytical continuation. And that actually makes a lot of sense if we look at this cartoon picture, because if you line up a bunch of masses decreasing in size and then kick it, of course the light masses will move more. That's all this is saying. It's this trivial example where we're essentially violating Newton's third law. But the point I want to get back to is, what about elasticity, right? Because there we actually have conservation of linear momentum for one. Also, it's in the continuum, so it's not as clear what will happen with the boundary. So let's check it out. So if we took something that looks like this matrix, which I introduced earlier, I set the A to 0 just to keep things simple. And I'm going to consider a cylinder, so open boundaries at the top and bottom and periodic on the left and right. And my dynamical matrix looks like this. I can compute the eigenvalues. And I'm going to resolve it in terms of a Qx and a Qy. And let's look at a few cases. So if K naught is 0, we know that this thing is Hermitian, so the spectrum lies on the real line. If I increase K naught a little bit, progress, I can go into the complex plane. But you notice that if I'm doing this as a function of Qy, it's just going to trace out a line, right? Because there's no interesting Q dependence actually inside the complex number here. And if I were to go to K naught being extremely large, this thing would lie along the imaginary axis, which is just as bad from the point of view of skin modes as lying on the real axis. So the skin modes were killed, and they were killed by a reflection symmetry ultimately, because if I have these two, because when I go to Qy goes to negative Qy, I recover the symmetry. That means every mode already has a partner. I'm not encompassing these open loops that can contract and cause the skin effect. So, but let's try a little harder, right? So we know that the origin of the problem has something to do with having too many symmetries in the reciprocal space. So let's see the effects of anisotropy. So the previous one we looked at was isotropic, but let's consider a simple example with anisotropy. So I've coupled dilation and shear, and that coupling, if you go through, kind of looks like this. And you notice we're making progress, right? Because if you were to take a single line here, or it's even more clear if you look at the bottom row, and reflect it over a horizontal axis, we notice that the input will get flipped, but the output won't. So at least we're breaking some reflection symmetries that we didn't break before. And then here's the dynamical matrix, if you're curious. And indeed, we can do the same three cases. We could do only the symmetric part, this GE, which is symmetric. And what we find is there's no localization. So what I'm plotting here is the cut boundary, and then I'm plotting the displacement field in terms of a color map. And what we see is the intensity is constant, right, over several wavelengths. Similarly, if I do GO only, one interesting thing is that you see that the displacement field begins to cycle. You can see that in the color scheme, but indeed I have no skin effect. This is still an extended mode. But when I have a mixture, I get both those cycles and a localization to the boundary. So if we compute the spectrum by finding the eigenvalues of this, the black lines here are the analytical calculation for for periodic boundaries. And they indeed trace out these open arcs. They have regions that are completely non-redundant. And if you were to numerically compute the spectrum with boundaries, we find that indeed there is a strong difference between the periodic and the open bound conditions. And this difference in the spectrum is also corresponds to a very strong degree of localization that's extensive in the number of modes. And then finally, this is real quick. I know we're running out of time, so I'll just go quickly through this slide. I mentioned topology in the advertised version of my title, and I didn't want to get accused of false advertisement. So there actually are some very interesting topological features if we not only consider the continuum, but also a microscopic model as well. So here I have 3 samples, and what I'm going to do is I'm going to go from being a Hookean spring to one where the force is entirely transverse, and I'm just going to take a honeycomb lattice. I'm going to poke it. These are overdamped dynamics. At first, nothing much happens because it's overdamped. Still not a lot really happening, but when we poke and we're all the way transverse, what we notice is that there's this very robust edge state that that doesn't reflect, doesn't go backwards, and it's completely unidirectional, confined to the boundary. And so we can do a little band theory to see what the origins are. Way down here at theta equals 0, we have mechanical graphene. And if there's one thing you know about graphene, if you've ever looked at the Haldane model, for example, is that it's not topological. One of the issues with the not being topological is this time reversal symmetry, right? So if here's my dynamical matrix originally, it has this time reversal symmetry, which in the case of mechanics just comes from the fact that the forces and displacements are real. Now I can write this entire dynamical matrix for all the cases as the sum of 2 pieces, the dynamical matrix at 0 and the dynamical matrix at pi over 2. And you might think, okay, obviously this perturbation we're adding must break the time reversal symmetry, but it actually doesn't, right? It keeps the displacements and forces are still real. So we keep this naive interpretation of time reversal symmetry. Instead, we're going to break hermiticity. And so unlike the Haldane model, for example, where these Dirac cones just split and open up, instead, they actually press into each other and form these lines of degeneracies, which are known as exceptional rings, that actually correspond to defectiveness in the of the Hamiltonian. And when we go all the way, we see not at an infinitesimal value, but all the way at a finite value of theta, the gap eventually opens, and we're left with 2 topologically charged bands. You might ask, did we cheat? Well, no, not really, because if you consider this object, which is just I times the dynamical matrix at pi over 2, this object actually is Hermitian and violates time reversal symmetry. And I say almost because you have to restrict it to its optical modes for the hermiticity, but that's a small detail. And it's also fun to play with other lattices where this is a Kagome lattice. You can see that there are these topological modes that wind between different bulk bands. And we can deform it, break certain symmetries. And then in addition to the topological modes, we get this extensive number of localized modes indicated by the bright yellow color. And these are actually skin modes. And you can see that they just qualitatively have a very different character than the topological modes. So with that, I think I will stop talking and ask if there's suggestions or any other group meeting like activities.
So I have a quick question. So there's well, I guess the same words are used for or similar words for like odd viscosity, which have been found in materials that or where one injects energy into the, I think William Irvine is working on something similar to that, where he's like, there's an extra source of energy where they're rotating these like particles that comprise a fluid. Is it related to this odd term? I guess that they have an odd term in there, is stress tensor as well. So
yeah, it's exactly related. So let me stop sharing my screen and let me have a whiteboard behind me. It's you guys can see my handy dandy whiteboard, right? Yeah, so if you were to think about the stress tensor, what I just described was Cijmn times the strain, UMN. But you could also consider a coupling to strain rate, which is U dot Mn. And this term here is the viscosity, right? And that term can also, it can also be antisymmetric. But if you were to open a normal fluid mechanics textbook, they'll also tell you that that should be symmetric, right? They tell you that these things should not be there. But the reason for viscosity is actually physically much different, right? So the whole ordeal that I spoke about was related to energy conservation. And we had this quadratic free energy, but we're saying there's energy injection, so we're not confined to the existence of that quadratic form. For the case of viscosity, it's not actually about the energy. You don't need energy injection. What you need is the relevant thing there is an entropy functional, right? So the way that you would normally derive the symmetry of the viscosity tensors to say, okay, I have an entropy generation functional that's quadratic in the strain rate, and the Onsager reciprocity theorem says, okay, if entropy is bound to increase in time, then you should be at a local minimum of that. So you go through the same arguments and you deduce the symmetry of this viscosity tensor. So there's a lot of words. I don't know if it's very clear. But there, it's really about entropy is serving as an arrow of time. And so the crucial ingredient there is not energy injection, but actually time reversal symmetry. And so the key ingredient in these odd viscosity systems is the breaking of microscopic time reversal symmetry. So you can actually observe some of those effects in plasma, in which you have a two-dimensional plasma, let's say, you have a magnetic field which will break the time reversal symmetry and but actually conserve energy. So there's a structural similarity, but physically a very different source of the breaking of the major symmetry. Yeah.
Thank you. That was really clear. Thank you.
Yeah, no problem.
Okay, I think I'm going to stop the recording, but if anyone has any more questions, please ask them.